the president of CMG, Kevin Mobley, and he'll talk a little bit about CMG. And again, thank you so much for your partnership in this area. And thank you, Darren. Everybody's in this. Okay, great.
Cool. Thanks, Nalini. Hi, my name is Kevin Mobley, chair of the Computer Measurement Group. The organization itself has been around about 40 plus years, and we started because of the enterprise. The concern back then was people were buying big mainframes and they were having lots and lots of problems, and people were coming to CMG figuring out how to save millions of dollars in a few sessions. So that was the genesis of the organization. Fast forward today, why are we here involved with Nalini is because it's the same issues, right? The things you talked about performance monitoring, about how do you basically track down, where issues are. If this goes through, and a lot of our folks that come to the organization, plus myself, I've been in performance for 20 years. And I quickly understood when she was talking about this, how much impact this is going to have on the work that we do with a lot of our customers. We work for a lot of big banks and folks in the airline industry and the like. And I knew right away this was going to be a huge issue. So that's why we decided that this was a perfect partnership for us. And so we're real concerned about this. And this is an example of what CMG today is about versus what we were about 40 years ago. Some of you may have heard of the organization. A lot of people associate it as a mainframe performance capacity group. Today, we're a lot more than that, and we're growing in that direction of being a lot more. I'll just give you a quick highlights, and then I'm going to move on and let you guys get to the actual meat of the presentation. We've got Ed coming over from Netflix, and I love this presentation because he's talking about how they rebuild their data center pretty much daily. And I think that's a pretty powerful presentation. I've heard pieces of this work before. I think anyone who is interested in sort of where the data center is going, I think that spending some time listening to Ed is pretty powerful. We've also got Kevin coming in from Capital One, and those guys are always. I've done a lot of work over there in my own company for years, and they do a lot of it. They're a pretty tech savvy company, and so I think that folks that have a chance to come listen, this guy is going to be pretty impressed. And then of course we cover a lot of stuff around data. I mean, CMG's roots is data. And then we've got about 80 other presentations that are going to be there. And a lot of professionals in our space are going to be talking about the kinds of issues and challenges. We've got a big contingency coming in from Brazil. They're going to be bringing a lot of their perspective. And so we always learn a lot from each other. So I encourage you guys to register, come out to the conference. Just scroll down. Okay. All right. One of the new features and far as I can tell, I don't think there's much of this being done in the performance space anywhere in the world. I know of a couple small examples of hackathons. And why is this important, right? This has historically been a developer thing, right? People say hackathons, they think about developers building some cool new app or whatever. I'm particularly interested in this because we are trying to find a way to get people real hands-on experience with a lot of these tools and processes, things that they don't necessarily do every day in their day job. We're trying to expose people to a lot of things. And so and we're also trying to crossbreed not only the more hardcore performance capacity folks, but people in the development community as well. We've optimized a lot of code over the years, and I've always told people the best developers in the organization typically work as part of my team because that's what we end up having to do. And so we're taking this as an opportunity. We partnered up with a company called Angel Hack. They run the biggest hackathons in the world, and they've got about 100,000 developers in their database. And so that weekend, we're going to be doing, a lot of interesting stuff around blockchain and IoT and even drones. And we're going to be the common thread running through all of that. It's going to be performance capacity. So definitely encourage folks to come out for that piece as well. And then, of course, there's money involved. All right, so I've talked a little bit about the organization. I told you what we're about. I'm going to be around all day. Would love to talk to anyone individually.
Okay, so I have a question. Great if anybody can make it there this year. Many of us work in a corporate environment where we have to forecast for the next year. Can you share where the next one might be?
Yeah, we're gonna be in Seattle. Okay. And right now it's slated for the first week of November is our standard date for the conference. If that shifts, we'll let folks know. But Seattle right now is where we're going to be. But in addition to that main conference, what you're going to start seeing out of CMG is a lot more of this. It's not going to be just one major conference every year. So there's going to be work done at the regional level. There's going to be day events. They're going to be very events around specific tech. So we're going to be doing events around blockchain, events around very specific things, not just trying to roll it all into one gigantic conference every year. But the conference itself will always be right now in November, and it's going to be in Seattle coming up next year. Okay. So cool.
just mention, if you guys haven't been to, there's a local CMG as well. So I was just at the last one. Tom Bichetti leads the local meeting. And like you said, it started out in mainframe storage and other things, but they're evolving. So I think, you know, we have the performance engineering roundtable as well that a lot of us like to go to, but a good opportunity to learn some additional things.
Mm-hmm. Cool. All right, thanks, Nalini.
Thank you so much, Kevin. So let's start. What I'll do now is I'll go ahead and start with some of the technical stuff, and then we'll go ahead and take a break. What we're going to have is I'll talk about, I'll give people a level set on what TLS is, so that when we start talking about Diffie, Hellman, and, you know, RSA, like, what exactly do we mean? And like when you do static Diffie Hellman, there will be a test. No, just kidding. So yeah, so you know, so do it so that we can all kind of level set and be able to talk. And then Steve is going to talk about the exact impact on large data centers, and he'll do the presentation that he took around to groups of people at TLS. You know, all over IETF, you find groups of people clustered around Steve when he walked through them. That was crazy. So, okay, all right. What are we talking about here? We're really talking about what goes on over the internet, because TLS is an internet protocol. One of the interesting things, of course, is a lot of people in large enterprises think, I'm an enterprise, I do intranet. What does the internet have to do with me? Well, the problem is, and it is a problem really for the IETF as well as enterprises, the exact same protocols are used quite often. Every once in a while, there's a little bit of this is for the data center. In fact, like for example, there's a data center TCP, or there's like certain things in IPv6 which are for a particular administrative domain. But by and large, the exact same thing that happens on the internet happens on intranet. And of course, the internet is everywhere. And since it crosses borders, if we had something like this, I know that whenever you go somewhere, you know, if you go to Europe or Asia, you're always carrying around your little electrical converter things, right? And then of course you get the wrong one. But anyway, it's like if the internet worked like that, if we had a different socket or a different kind of protocol, every time you switch, you cross the border, well, it wouldn't work. The internet just wouldn't work. So everybody's got to use the same thing. If you're in the Sudan or if you're in Seattle, it's the same thing. And really, how does this even happen? In fact, what people say is the disruptive innovation that has formed the internet is protocol standards. That is the disruptive innovation that allows the internet to function. Everybody uses the same standards. And who does that? Well, it's a group of engineers. It's an informal grouping of engineers, if you will. And I suppose that's somewhat disingenuous, because there's a real core group, and they are probably, most of them are supported by companies. But the very fundamental reasoning behind the IETF is that you represent only yourself. You do not represent a company, because the fundamental reason for that is they want somebody who is not from some huge organization, but has really good ideas to have a voice. So that's the aspirational goal behind the IETF. And sometimes it even happens. So it's not bad. And you know what? I'm going to put a caveat here too. How do I say, truth in advertising. I'm I'm split. My loyalties are half IETF and half enterprises. Not that there should be a conflict. I represent both sides. In fact, I was just nominated to be a trustee of the IETF. So it's not that. I have a lot of loyalty for the IETF, and I will be asking for your vote. So anyway, I believe very, very strongly in the IETF, and I believe very strongly that the next step for the IETF is for enterprises to become involved in it. So what does the IETF do? Meets 3 times a year, and it has to meet all over the world because the internet is all over the world. And just like all of us don't necessarily like going to Singapore, people in India have a really hard time coming to Seattle. It's just as expensive for them, and more because they're, the exchange rate. So anyway, it's all over the world 3 times a year. There are over 120 working groups right now. It will probably grow. It will probably grow as the internet permeates more and more things. And because, as I said, one of the things, just internal IETF things is like we're not having 2-week meetings. And so what do you do about when you start getting, there's already too many tracks. Anyway, there's over 8,000 RFCs that have been written. In fact, we're in the 8,000s right now. And each of these is blood, sweat, and tears has been spent over most of these to get them. And interestingly enough, there's people at the IETF that you'll meet who have a pretty good idea of what most of those 8,000 do. It's actually amazing. Some of the smartest, most interesting people I've ever met are at the IETF. No, it's crazy. It's just crazy. So what kind of standards? Well, everything, TCP, IP, all of it, TSL. Basically anything above layer 2. Now, there are some interesting sidelights. There's people who are talking about, well, if you walk away from IPv4, is ITU going to take it over? There's some interesting discussions. Basically, the idea is IEEE is going to do layers, 1 and 2, and we'll do layers above that. There are some liaison committees for, layer 2.5 or what happens when you have, some of the interlayer communication kinds of things. And there are other standards organizations, ITU, ETC. Bill is going to talk about ICANN, another policy-based organization. There's a lot of standards, and every single one of these is complex. It's a huge amount for any one organization to keep track of. It's just huge. And we will talk at the end about something a way that we're trying to figure out to get a handle on this. So let's get to what we're here about to focus on is one problem in one protocol in one working group. We're talking about a 1-sentence change, which is likely to be a multi-billion-dollar problem. So, and what is this thing? It is the thing about eliminating RSA key exchange. And so we'll talk about exactly what does that mean, how do we do it, and what are we going to, and why. So what we do today, what these guys do, US Bank and everybody, many people, is, you'd like not to have malware and viruses all over your user community inside the data center, et cetera. You'd like to do a little bit of fraud detection and not have leakage of data. Well, how do you do it? Oftentimes, you have to go inside the payload, and Steve is going to do a lot of talking about that. You cannot just look at the header data, what's called metadata. It's not possible because the actual problem, let's say, for example, the DNS name of what you're exfiltrating out to is inside the payload. You just can't do it. I'll give you one quick example of what that happens. And as I say, Steve's going to talk a lot about what we need to have, which is called packet decryption. Means looking inside the payload of the packet. And the problem is the way we look inside the packet today is using something called RSA key exchange. I'm going to explain what that is and what's changing about it. Essentially, the problem is we won't be able to decrypt. What we do today is we have large data centers with all kinds of things, servers, load balancers, et cetera, middle boxes, endpoints, and so forth. In fact, I know some people who have 15, 20, in fact, I've heard like 80 different points from one path to the other. There's just a lot of things. And what we do, oftentimes what we do is we have passive out-of-band data capture, because if you had every single server, every load balancer, every firewall keeping its own data, one, they're not even meant to handle that, and you drive them to its knees. I was working with somebody the other day, and we put a load balancer in trace mode, and in a minute and a half, it was on its knees. So you have passive, large data capture devices, and we'll talk about some of that and how it's done. And what we do with all that data is we look inside the payload. So let's just talk about decryption. For example, if I send something like this, if I send a little Google screen, and it's got the Google logo and it's got the search box. On the other end, I just get the Google logo. And I'm like, I don't even want that. All I want is the search box. Where'd my search box go? In which of the 80 hops did it get lost? So what you have to do, you go, is it here? Is it here? I'm sure you guys have been on those kind of calls. I've certainly been on calls with 35 other people on the line. Of course, each of them saying, it was not my fault. But anyway, but you know, all those things, where did it get dropped? So you have to know, where did it get dropped? So how does not being able to decrypt in between impact you? This is an interesting little screen that some of the people that I work with, some of the enterprises we work with closely, I just said, guys, you know, you give me what you think is going to break if you can't decrypt. And they said, of course, internet banking, insurance, you know, what am I doing for HIPAA, stock trading? These are all people I know 100% because I work with them daily and talk to them who are doing out-of-band decryption like this. And really, they said, you know, anything that's anything that's doing internet, facing the internet or doing decryption is going to break. And why? Because instead of taking 4 hours or 2 hours to decrypt the problem, or to solve the problem, it'll take 2 weeks. And then in that 2 weeks, when internet banking is down, your customers just walked over to the bank next door, right? So there you go. Yeah. So the question would be, this is so stupid. Why would the IETF even do something like this? Like, what are they? It's like, you know, I mean, what is wrong with them? So let's talk about what is RSA key exchange exactly, and how does it work, and why was it deprecated? Basically, RSA key exchange uses private key, public key algorithms. What you need in this kind of thing is, if you have the private key, it can decrypt what the public key decrypts, and vice versa. And the private key, of course, you keep very, very secret. You don't tell anyone about what the private key is. And the whole essence of this kind of algorithm relies on the safety of the private key. It also relies on the other thing, one other thing, which is that it's computationally simple to derive the public key from the private key, but extremely difficult to derive the private key from the public key. Very difficult to go. In fact, it could take maybe months or sometimes years of computation to do that. And though the public key algorithm that we're going to be talking about, that's very often used, is RSA, developed in 1978 by Ron Rivest, Adi Shamir, and Leonard Edelman, hence RSA. Now, I have to say, when I first heard about this, I'm like, no, this cannot work. Or how does it work? My mom is a mathematician. And so I said, all right, mother, explain to me how this works. And she did. And so now I'm like, okay, I get it. Because basically what you're saying is like you have a key, which is flowers, and it decrypts something, which is tiger. And you're like, what? How could that even work? You know, it's like, but there has to be a mathematical relationship between those. That's the only reason it works. It relies on two things. And I'm gonna kind of flip. I'm gonna show you these because they're integral to RSA and go past it. It relies on two things, which is hard to invert functions. You'll hear that a huge amount in cryptography, something that's hard to invert. For example, if you do addition, 1 plus 1 is 2. If you want to invert that, what's the inverse of addition? Subtraction. You go backwards and you can get the other one. But there are certain functions which are very difficult to invert, and those are used quite often. So let me give you, for example, if I give you the number 2 and I give you 4, you're like, you're doubling. If I give you 5 and then you give me 10, okay, you're like, that's pretty good. I give you 9 and then you get 18. That's very clear what I'm doing. So you can go backwards on that very, very clearly. Let's take something which is not so easy. It's like if I give you 2 and you give me back 1, okay? You go, well, maybe you're halving, all right? And then you do 5 and then 2. You're like, okay, maybe you left off the remainder. How about then you give me 56 and I give you 35? What's the relationship between that? There's no pattern. That's very difficult to deduce. You notice that with a 2-digit number, if I didn't give you the answer underneath, I've done this for a lot of people and not given the answer. Everybody's like, what? You know, and you can't tell. You don't know what that is. It takes a while. Essentially, I'm using a couple of things. I'm seeding it and I'm doing modulus. Modulus, or the remainder function, is very difficult to invert. That's one of the, there's a number of those kind of things. Modulus, exponentiation, and also something called prime number factoring. Prime number factoring is very difficult. As I say, I had to have my mom write all this out for me. And so she's like, refresher on prime numbers, okay? The smallest prime numbers are 2, 3, 5, etc. A prime number is divisible by itself and 1. No other, like 4 is not a prime number because it's divisible by 2, but 5 is. 5 has no smaller divisor. So when you do prime number factorization, you just take all the prime number factors. Like all the prime number factors of 8 are 2 and 2 and 2, 3 times. Oh, about 15, 3 and 5. Very easy. But if we start getting into bigger ones, the reason this is hard to invert is because there's no formula for it. There's no formula. It's done by brute force. There's only a brute force thing, a brute force way. If you look at the example of the formula for RSA, and again, I'm not going to go through this, is you'll see that what they're doing is prime numbers, modulus, exponentiation. These are all the things that they're doing. And they put one time they wanted to crack RSA, so they put this very large number out there. They said, okay, go ahead and factor that one. And it was done 17 years later using a whole grid system. So for a long time, people thought RSA is safe because they could not factor prime numbers that big. All right, so fast forward now to something approaching today. You'll probably have heard of something called quantum computing. And this is moving extremely rapidly, actually. This is actually very, very quickly. There's quantum ciphers, which we actually should think about, but I'm not going to think about that right now. There's, you know, they say too much to think about, but the Chinese are working on quantum ciphers and have done quite a bit with it. Anyway, it's a way to very quickly do certain kinds of computations, in particular mathematical computations. So there's a guy at MIT, Peter Shor. He came up with an algorithm to factor prime numbers. So now why you're like, aha, now you're starting to see why I went into this prime number thing to start with. Because if you can factor prime numbers with a computer or algorithmically, brute force is gone. Now you're on it, right? Now you can do RSA. So for quite a number of years, I remember at the IETF, this was talked about, that this was the reason. It was before the NSA revelations. Before the NSA revelations, a lot of the chat in the hallways was like, when is quantum computing going to be able to crack RSA? Because the next thing that happened is this guy, Isaac Chang, an MIT physicist, he actually was able to build a quantum computer. Because it's one thing to have the algorithm, well, I got nothing to do it on. Well, so now here comes this little team, and they're doing both. But what have they done? Well, they've managed to factor 15. And many high school, not all, I suppose, but many high school age children, some elementary age children could factor 15, right? 5 and 3. And so you're telling me you need a quantum computer be able to factor 15? Grand. And two guys at MIT, wonderful, wonderful. So anyway, they're moving very, very rapidly. I think they're now up to a 5-digit number. But frankly, watch this space. Things are going very quickly, and there's a lot of money, and you can imagine from whom, going into this area. It's very, very interesting, and it will be extremely useful. But actually, why invent when you can steal? So what actually happened, and you know, anyway, this is all very unfortunate. What happened is what a lot of people did, and it was unfortunately some of our intelligence agencies, both in the United States and the United Kingdom, they stole a lot of keys. And this was revealed by Edward Snowden, which led to an RFC, which I think has gone a little far the other way, which is saying pervasive monitoring is an attack. Because what did the NSA do? They monitored wholesale monitoring, grabbing of data. As I say, I'm not giving you my opinion on whether it should have been done, whether it needs to be done, or whether I even think lawful intercept is a good thing. I'm just telling you these are the facts. This is what happened. This is the history of why, who did what, and why RSA was deprecated. This is what happened. And so the Snowden Revelations talked about some of the the manufacturer of one of the largest SIM cards, and they stole the private keys from Gemalto. And so there you are. There you are. It was a joint operative between the NSA and the British government. Here, it was, as I say, it was Gemalto. The references are right there. You can look them all up. They produced some 2 billion SIM cards a year. Their motto is security to be free. Here's a foil from GCHQ talking about what private keys are and what you do with them in order to break things. Again, I'm not giving you my opinion on lawful intercept and whether it needs to be done. What happened is after this, the IETF decided that they need to switch, that it was far too easy to get these private keys, which had to be kept secret. So now we're going to start doing something called forward secrecy. It used to be called perfect forward secrecy, but now it's like, do not use that word perfect, because nothing is perfect. There are ways, as I say, I'm not going to go into the dynamics of, because the other thing is, like, there's a discrete logarithm problem, which I'm having my mom write up so that I can understand it. Yeah, because that is how you can kind of break into some of the Diffie-Hellman things. But what forward secrecy now relies on is an algorithm called Diffie-Hellman, and that's what we're going to be using. So let me give you an understanding of Diffie-Hellman, so we'll all kind of level set, because a lot of what Steve talks about and the solution rely upon Diffie-Hellman. So what is Diffie-Hellman and how does it work? So Diffie-Hellman ephemeral says you are never going to pass the key over the wire. Remember that in RSA we had two keys, private key, public key. In Diffie-Hellman, really there is no key. We call it a key, but there isn't. There's something else. There's no, each end knows something. Both ends calculated. And so again, it's kind of like, you're like, what, how does this even work? Okay, so back to mom. Actually back to Wikipedia too. Wikipedia does a really good job on this. So let's just kind of walk through this. Is basically you agree to use something which is a modulus. Remember some of these basic arithmetic things called modulus, that's gonna come in handy for us. We decide on a modulus, let's say 23 and a base, which is 5. You had to pick them specifically. You can't just pick any old number. You have to pick those two things at a, at a reasonable point. But once you've done that, then you have Alice and Bob. And what Alice does, let's say it's the client, he picks a secret integer, let's say 6, and then he calculates something, which is G to the, if 5 to the 6 mod 23, which equals 8. So he sends the number 8 over the wire. And then Bob does the same thing. So the two ends have both chosen a secret integer. They do a calculation, send the calculation over the wire, and then it's inverted at the other end. And then lo and behold, you come out with the same number. It's crazy. It's literally crazy. It's like, how in the world could this even work? But it does. Here's I like the color one. So let's say you start with yellow. So you start with the base. Everybody has to agree on the base. And then I pick orange, you pick cyan, and then it gets into a certain color. You pass that color over the wire. So anybody over the wire, all they see is you've passed taupe and blue. I can't do anything with that because I don't know the base and I don't know your secret integer. You know the formula. Diffie-Hellman formula, I mean, that's been there for years. And then when you invert it, you both get green. And that's the idea, that secret thing that you get. This is the essence of Diffie-Hellman, is this. And so you see now there's no keys. There's no public key. There's no private key. Nothing is passed. Everything is one shot and then it's gone. So there's the problem with that, of course, is one and done, is there's no way to go back to something that was done after and then decrypt it. So this is wonderful for privacy and secrecy, but for network management and diagnostics, this is a death knell, right? I mean, what, right? How do you do it? How do you do it? So now I'm going to give it over to Steve. No, Steve will explain how we do this. So that's the problem. And when you go into the RFC, you'll see actually Eric Rescorla. Eric is, again, one of the most interesting people you'll ever meet. He's like, what, 6'8", has always wears a baseball cap. And if you think I talk fast, I mean, he talks like probably 3 or 4 times faster than me. And he's he wrote TLS 1.1, 1.2, and he's the lead. He's the main author of 1.3. Adorable, but you know, he also wrote, like, what they did was all the G mod P whatever, they've done an RFC where they have public key and private key versions of which one is what. So if you actually want to go through and look at that, that'll be that. So as I say, sorry to get so technical, but we need to have some level set on what RSA and Diffie Hellman are, because otherwise what Steve is about to say and the solution aren't going to make sense.